Hello, I am Agista Hidayatillah, and now I am presenting my research with the title is Faulty Input Summarization in Data-Intensive Computing Using LLMs. Nowadays, data analysis requires dealing with terabyte scale of data. This data usually spread across multiple machines, and to manage the complexity of this data, we rely on the ISC or data-intensive scalable computing. The tools is like Apache Spark and then Google MapReduce, then it can make easier the data analyst or programmer to run the program or write the program to manage the distributed data efficiently. While we are working on the ISC system that can be used to manage a huge volume of data and combined with the distributed nature of this program, it will be very challenging to debug on the system. Imagine if we have a program to evaluate the average of annual rainfall in United States. It has to average the tens of millions data points from sensors all over the country. And when the program ran, then unexpectedly the result is error. So how the programmer or how the data analyst discover or figure out what's gone wrong here? This kind of problem makes debugging on the ISE application is so difficult. Many efforts on debugging program aim is to reducing fault-inducing input size. This technique is a variation of delta debugging algorithm. This algorithm works by repeatedly running program with different part of faulty input until convergent into the smallest problematic input. However, this technique doesn't work well on the ISC system because we know that the ISC manages a large scale of data and all of them are separated on different parts. So if we implement repetitive work on the ISC system, it will be very time consuming and costly. Therefore, we are introduced FISM or fault-inducing input summarization. This is LLM-based technique to summarize faulty data. And our techniques also involve pre-train the lightweight version of GPT language model, which is Distill GPT. And this unsupervised step also allows our model to learn the basic structure and the pattern of the large-scale data. And also we are combined with the Titian. This is a library from Apache Spark that can be used for searching data provenance from our program result. Okay, this is the workflow of FISM. Let's say we have input data sets, and we also have the ISS application in Apache Spark. This application can filter both correct and incorrect output. But because our research goal is to debugging the data, we need to discover what is the incorrect output of this program, right? So let's jump to the phase one, which is identifying fault-inducing input. In this phase, Titian contributes to track the data provenance of this incorrect output. And then it will be saved on fault-inducing input database. Next is training language model. In this phase, Distill GPT model will train all of these fault-inducing input. And then the last phase is fault-inducing input generation, which is the Distill GPT model will generate the faulty input incrementally here. So this is the implementation of FISM in our research. We implement FISM on 16 benchmark program, and all of the program input we set are the same, which is 10,000 rows, and the failing output is the incorrect data for each program. And the data reduction is how many FISM can summarize the following output, and then the fault detection rate is how well FISM will detect the correct failing output. Okay, we are doing evaluation on our research by providing 4 questions. The first question is, does the summarized faulty input from FISM retain the fault detection capability? So here I pick one case study, which is delivery fault. In this case study, the fault in the sync inputs is 1559 rows. And then the fault detection rate here is 100%. We gain this value from re-implementing this FISM result to the delivery fault program. So if the delivery fault program output result is the same with the input, which is 16, so the fault detection rate will be 100%. This also works with the 32, 78, and so on this program, and the average is 100% correct. The second question is, how much reduction in faulty input can FISM provide? So the data reduction is highlighted with the yellow color here. In this research, we categorize as 6 different percentage. So from this data, we know that only with 1% of the failing output, we can already know what the kind of data that is triggering error in this program name, in this program line for this case study is edge analysis. So this is very efficient to data analyst or programmer. Then the third question is, how long does it take to generate summarized faulty input? Once again, I remind you that the goal of FISM is to minimize the fault isolation time. So from our experiment, we illustrate on this table that FISM successfully generate the summary of faulty input in less than 1 second for each row, all over these case studies. So this is very fast and efficient. The last question is, how long does it take to train an application-specific model by FISM? So in this experiment, we will use the laptops without the GPU to train the distributed model. So this is our result on FISM model training. The highest is 30.5K seconds in program 16, which is WordCon program, and the lowest is 103 seconds in the second program, which is commute time. So the conclusion of our research is we are introduced FISM that can reproduce the IIC application errors with much less data. And based on our experiment, FISM is able to reproduce the original fault in less than equal 1% of the original fault in the sync input size. And this research also highlight that using language model, it can reducing fault inducing input to adjust few sets of rows. And also, even we are only use the lightweight version of GPT, we can get higher rate of fault data reduction. And also this can be run on local system, and the debugging is very interactive, which is otherwise invisible on large scale data. So this is presentation for me. Thank you for attention.